Okay, so let's go on to this first one. Well, what are we doing? Analyzing more complex op-amp circuits. If you guys can do these problems, then next week's quiz will be a breeze. Okay, so and we want to apply our learned analysis techniques to more general op-amp type problems. And that's pretty much it. That's what we're doing today. Best way to learn is to actually do it. All right, so here you go. I don't need to talk too much today, which is great. Here's the first problem. Log on to Melts, and this one should be a nice warm-up, because essentially you should already know how to do it. Find the gain and I/O. Okay, so in this case, we haven't talked about finding what the currents are, but you should be able to put together all the little bits and pieces that we've used up to this point to figure this out. So you've got, in this case, which we hadn't done before, we've got specified values of voltage, resistor 1 and resistor 2. So go ahead, use the methodology we did yesterday. Is the circuit in negative feedback? If it's in negative feedback, I want to relate some quantities to each other. As you're doing that, what do you need to do? Well, probably need to write a Kirchhoff's current law equation somewhere along the line. Yeah, Kirchhoff's current law equation. Should be getting pretty used to those. And in actual fact, you'll find you'll use it throughout ENG1030. So this might be a typical test problem that you might take about, I don't know, 5 minutes to figure out, check over your answer again and again and again until you're satisfied with it. Couple of ways you could do this. You could look at the circuit and your memory might get jogged and you might have memorized the gain equation for this particular circuit. You might recognize it as a particular type of amplifier. So we've covered inverting, non-inverting, and a summing inverting amplifier. So you might know the gain equation, which helps you to calculate the gain. If you're like me and you don't like memorizing lots of things, then I would remember the basic principles of how to do it from scratch and do it from first principles. melts.eng.monash.edu. No worries. Does anyone not have access to Melts? Okay, because I know some people enroll a bit late, so we haven't added them into the course. Just in case you did, let me know. Yeah, feel free to talk to your neighbours about this. There's no such thing as too much collaboration in this case. And this is really for you to get an idea of how you're tracking along in the course to this point. Okay, how are we tracking for time? Who needs more time? Okay. Another minute or so then. Not many people. Okay, anyone need to record something in Melts? Here's your chance. If you've got no idea, just put something so that you at least get the participation. All right, so we're getting up there. Yeah, getting to nearly everybody usually. Take your best educated guess if you. All right, so 5, 4, 3, 2, 1. All right, so I'm locking that now. And let's have a look. What's going on? And we have vast majority of people reckon B. Gain is 7, I/O is 0.6. People reckon also gain is 6, I/O is 0.5. Less people think there's negative gain. Okay, so how do we go about this? All right, so first things first, negative feedback. Yes. So therefore, V plus equals V minus, which we can say equals what? V in, yeah? Because that's V plus, that's V minus, okay? So now, how do we calculate the gain? Well, you look at the current, I1, I2, I minus, and we write KCL. KCL, so let's call this node A, at A, gives us I1 plus I2 plus I minus equals 0. So I1, now remember how we calculate the current defined in the direction of the arrow. You take the voltage at the node that you're coming from, subtract the voltage of the node that you're going to, source and destination, and you say, so this is basically A. Well, the voltage at A we know because A is directly connected here is V minus. Right, so therefore I1 will be V minus subtract 0 over R1 plus I2, which is V minus subtract V out over R2 plus I minus, which is equal to 0. Very good, because no current flows into the input terminals of the op amp. Equals 0. Well, V minus is equal to V in. Right, so let's substitute that in there. So therefore you get V in over R1 is equal to, well, V in over R1 plus V in over R2 is equal to V out over R2. I'm taking this to this side. And therefore V out over V in is equal to 1 plus R2 over R1 after a little bit of algebra. Okay, so you might recognize this as our non-inverting amplifier that we saw yesterday. And now substituting in our values, here we get the gain, G equals V out over V in equals 1 plus R2, which is 20 kilo ohms, over 3.3 kilo ohms. And that's equal to 1 plus, this is approximately 6, round it to 6, equals 7. All right, so there we go. So if you work that out, you probably by deduction figured out that this was the answer. Okay? So how do we actually get this current? Even though you know that the current should be 0.6, where does that come from? So you've got I/O here, and we're asking you what that current is. Well, to find the current through I/O, that is the same. So let's get rid of all this marking so it makes it easier to see. So I0 comes out of the op amp, goes through R2 and through R1, right? Why do you know this? Because there's no current going through here. So any current that goes into R2 must also come out of R2, and the only place for it to go is through R1. So therefore, the current that goes through there is equal to whatever you calculate for V0 divided by the two resistances. That's one way to work it out. So we know V0 equals to the gain times V in. That's what gain is. Gain is V out over V in. And therefore this will be equal to 7 times, now we know V in is 2 volts, equal 14 volts. And therefore I0 equals 14 volts divided by R2 plus R1, which is equal to 14 over 23.3K, which is approximately equal to 0.6 milliamps. Note the kilo ohms, so volts divided by kilo ohms gives you milliamps. That's just a shortcut. If it's volts divided by ohms, this would be amps. Okay, so have we got any questions on that? Yep.
Yeah, for these questions, do we have to prove the gain formula every time?
No, so the question says find the gain in I0. If you can do that, good on you. You can say, I recognize this is a non-inverting amplifier and the gain equation is this, and hence the overall gain is this. That's fine. But if you make a mistake, then we can't, no, we, yeah, exactly. Yep, another question? Yes? Absolutely. So now, where you had a 0, so for example, I had a 0 here, you would have another variable or a number. And that will definitely change things. So, in fact, when you do stuff like that, you find that you start getting values which, so the output will be related to those two values. It'll be related to V in and the value down here. It just so happens that value is 0 in this case. Yep.
First case we found, we said that direction of I0 is up, then the second case down. Does it really match with this sign?
Okay, so this is a good question because it can get confusing. So why do I say I0 is coming out this way? It's because in the question that you're asked, you've been given a definition of the direction you need to find I0 for. So therefore, I do need to make sure that when I do my calculation of I0 in this case, I make sure that I take V0 subtract 0 divided by the total resistance. So using the same rule as I used to find the current through these resistors, I use that same rule to find in that direction. If I did it the opposite way, 0 minus V0 divided by the other two, you'd get a negative answer for the I0. So it does matter because it's already defined when you're asked the question. If it's not defined in the question, then you're okay to try to figure it out and then subsequently figure out what direction things are really going in. But if it's defined in the question, you have to work it out if it's a negative value or a positive value. Okay? Any more questions? Okay, no? Let's move on. Okay, so what is a key takeaway message here? Key takeaway message which we touched on yesterday is that op amps will supply current from the output terminal as required to make sure that, so I should qualify this by in negative feedback. Op amps will supply current from their output terminal to make sure that the voltages on the positive terminal and the negative terminal match. So what's really happening here is that the op amp is adjusting the exact amount of current coming out of here to make this voltage at V minus equal to whatever voltage it sees at V in. And that's basically how the op amp works when you've got negative feedback. If you don't have negative feedback, the op amp doesn't know what's going on, and it can only operate in that mode that we saw yesterday, on Monday, which is that differential mode. Okay, so that's the takeaway message here. Any current that you see when you're working out with op amps is really coming into or out of this output terminal. And in addition to that, that current is really coming either from the supply terminals. So you've got that VS plus here and the VS minus here, those two supply terminals. So you connect some external voltage to those supply terminals, and that's really where the current from the op amp comes from. But the op amp will do smart things to get the exact amount of current required to make V minus equal to V plus. And that's what is really happening. Okay? Just to break things up. So who uses an Android device here for their access? Who uses iOS? Who's using a laptop or a tablet? Okay, so a few. Just announced yesterday, which I found really interesting, was that Android are now extending to wearables. So they're basically extending their software so that's got a nice interface on wearable devices, which include smartwatches. So you may or may not have heard of smartwatches. There have been some clunky attempts at this over the years, but this was really quite interesting to see that Android is making quite a play for it. This is actually a smartwatch that Motorola announced yesterday. It's called the Moto 360. And I think it's probably the first smartwatch that I would actually consider using and buying because it actually looks like a watch, right? Whereas the other ones, you know, I don't know if you've seen them, they're like big rectangular chunks on your wrist, like the Pebble or whatever. But the interesting thing here is, have a think about how much engineering is involved in making this device. You need to think about the software. So that's the Android stuff. You also need to think about the electrical hardware. That's what we would design. You need to think about the mechanical side of things. How do you fit these things into, how do you fit all that electronics into a little package? You need to think about materials. What kind of materials do you use to make the band? What kind of materials do you think you make the watch face, the actual internals? And also, what chemicals do you use, say, for the batteries and all the processes that you do? Okay, just have a look, you know. I think just looking at a single device like this hopefully gives you a little bit of insight when you're thinking about these things into nowadays engineering in general is becoming really multidisciplinary. So even if you just do electrical or you do mechanical or you do civil, I don't see much civil in this one. But if you do any of these, you will be talking to other engineers from other disciplines. So even if you're thinking of doing mechanical engineering or aerospace or anything else, knowing the stuff you do in this course is really, really useful because when you're not going to be doing the electrical systems, but you need to understand when the electrical engineer who's talking to you is telling you about what's required, right? Okay, so that's just a little bit of a appreciation of that. Okay, back to it. Question 2. So, hop on. Have a look at this question. So this one is something you wouldn't have seen before. The first one was a nice, easy one. And have a go at this one. So we're looking for what is the value of VO and IO when RL is equal to 10K and VS equals to 0.5 volts. Okay, so you can sort of cut this a little bit short because you can see that what is this? Yeah? You just did it right. It's a non-inverting amplifier. So remember what the gain of that is? Equals 1 plus R2 over R1, which is equal to the ratio of V out over V in. Okay, so what we're trying to show here is you've got this non-inverting amplifier, and that's all great. I can now measure the voltage on the output, given I know the voltage on the input, Vs. But in reality, that's great. I've got the signal, but you will probably be connecting this output of this op amp into something else. And pretty much all devices will have what we call some sort of load resistance. Okay. Okay, so that's why we're looking at this particular one. So I'll give you some time to work that out, and then I'll talk about some of the implications of this. So have a think about this and see if you can figure out what VO and IO should be. Now in this case, IO is now, as a hint, IO now is entering this node out of the op amp, but how will it react to two different paths of resistance? That's the thing. So does anyone really get into audio here? Yeah. Do you have expensive headphones? And when you look at those, if you look at the specifications of those headphones, they will say how many ohms they are. Yeah. That value is essentially this load resistance RL. And so depending on that value, that may have implications for circuits you decide to use the headphones with. Okay, most people are at least figuring that the output should be positive or negative. Positive, right? Because we've got a non-inverting amplifier. So that splits you down to two choices. All right, so I'll give you another couple of minutes. So first you work out what the voltage is going to be, and then from the voltage you can work out the current that comes out of the op amp to produce that voltage. All right. So, last minute. Anyone? Any more answers? Give you 5, 4, 3, 2, 1. Pick anything. Ready? All right. Done. That's right. I actually should probably put a I ran at a time thing there. Okay, so what is the answer? Let's have a look. That's the other one. Yeah. Everyone's like, ah, what? Okay, so what we got? C. All right. So I'm a little bit worried about the person who picked B. Right. So you need to understand that the gain that you calculate is multiplied directly to the source voltage to give you the output voltage. Okay, so you clearly can work out that the output voltage is 5 volts, which is good, but what is the current? So most people think it's 0.67, and hopefully people worked that out instead of guessed it. Okay, so the gain you worked out quite easily as 1 plus R2 over R1, so that's 27 over 3 equals 10. Therefore, V out should be equal to 10 times Vs, which is equal to, we've got Vs is 0.5, so this is 5 volts. Woo! All right, so let's say we've got 5 volts here. From here, you've got current that goes this way, out. You've got current coming into this node, you've got current going down here, you've got current going down here. So, what do we do? What did someone who got it right, what did you do? What did you do? Did you get it right? Yep, so what was your thought process here to get 0.67? Yeah, could you just tell me? Tell me. What was your, you don't need to go numbers, just tell me what you're thinking.
IR, so we calculate R, which is R2, it's 1 divided by 1 divided by R2 plus R1 plus 1 divided by...
So you put these in parallel is what you're saying?
Yes.
You put these in parallel and you did V0 divided by, using Ohm's law, the parallel combination to get the current going through both branches at once. Perfect. It's one way to do it. What's another way to do it?
Make I0 like use Kirchhoff's current law at that point.
Yes, use Kirchhoff's current law at this point, and what does this then become down in each branch?
So like that one on the right is 0.5.
Yep, so this is,
Ohm's law.
yep, 5 divided by RL, which is 10K, gives you 0.5. So you go, this is 0.5 amps, or milliamps. And on this side, R2 plus R1 is 30. So you could then say this is 5 divided by 30, right? So this is 27, this is 3. So then this would be 0.1666, so I put 1.7 amps. So you could do that as well. Either way works. If you combine these, this is equal to 7.5 kilo ohms. And if you go 5 volts divided by 7.5, you get the same thing, 0.67. Very good. Okay? So, now, what about B and C? So I'm gonna just get you to think about this. So if the op amp can only supply a maximum current of 100 milliamps, okay, so currently, get it? Currently, we're drawing, yeah, good. You're on the ball. So currently we're drawing 0.67 milliamps, and you go, okay, that's nothing. This op amp can supply 100 milliamps, so that's great. So let's say I wanted to draw 100 milliamps out of this, then I could ramp this voltage up by a large amount. Okay, so if this current were 100 milliamps, what is the minimum value allowed for RL? Okay, so what does that mean? So what happens if I reduce RL? So RL is currently 10 kilo ohms. And over here on this side, you've got 30 kilo ohms. Let's say that's 30K. So if I start reducing this value, 10 kilo ohms, then, and this is, say, let's say we've still got the same gain, it's 5 volts. If I start let's say this is 10 kilo ohms, the current drawn is 0.5 milliamps. What happens if I make this 10 times less, make this 1 kilo ohm? What happens then? What current comes out? Sorry? A bit more, right? 10 times more. So you start to get 5 milliamps. You reduce that a bit further. Say this is now 100. So 1K. Let's say now this is 100 ohms. So you're starting to draw more and more current down this branch because the resistance is low. In fact, if you took this all the way to, let's just connect a short circuit here, then you would draw all the current out of the op amp through this branch. So the question becomes, how do I calculate the exact value of RL that gives me, what is it, 100 milliamps? Algebra. Yay! Okay, good. So RL, you can calculate a couple of ways. So this is RL. Yeah. So you could say, well, you've got 0.17 milliamps down here for a 5 volt source. So you've got 100 minus 0.17 milliamps. So let's just call it 100 milliamps coming down here just to be approximate. So therefore you could work out that this would be, what's RL? So you've got 100 milliamps is equal to 5 volts divided by RL gives us, so this is for B, RL equals what? 50 ohms, right? Approximately, give or take some small amount of resistance. Okay, so we've worked that out, part B. Great, you say. 50 ohms will draw 100 milliamps out of our op amp. What happens if we start bringing this smaller? Okay, so if RL is now 30 ohms, then what starts to happen? Well, the thing that starts to happen is that this thing can only supply 100 milliamps. So now the problem changes. We don't know that we've got 5 volts here anymore. All we know is that this is 100 milliamps. So now if I put 30 ohms here, right? Discounting the fact that you've got, well, actually we don't even know what the current going through here is anymore because we don't know that this is 5 volts at V0. So discounting what goes down this branch, because this is 30K, most of the current is going to go through this branch anyway. What is now the voltage V0 given that this is 30 ohms? So using Ohm's law again, so you've now got 100 milliamps pretty much, because very little goes down this branch, times 30 ohms. So V0 is now equal to 30 ohms times 0.1 amps, which is 100 milliamps, which is now equal to what? 3 volts. Now this is a problem. Yep, question?
Would the current have to increase across R2 to maintain the voltage drop so that V plus equals V minus?
Yeah, so you would think that, right? So this is where things start to run into the realm of reality. So in reality, what happens is that now, because the op amp can't actually supply enough current down this branch to make V minus equal to V plus, all of our assumptions start breaking down. Remember this negative feedback thing? We say it always makes V plus equal to V minus. Well, that's only true when everything's ideal and we're not doing nasty things to our op amp, like drawing more current out of it than is possible for the op amp to supply. And if we stick a 30 ohm resistor here, we're going to draw the maximum current out of the op amp, which will mean that V out can only ever reach 3 volts if we put this load resistor here. So you pick up a headphone and you plug it in. So this op amp is, say, the output amplifier for your audio. You plug it in and your headphone has an 8 ohm load on it, say. Then this means, well, let's say if this were 8 ohms, the maximum voltage out would only be something like 0.8 volts, which is totally different from how you designed it, where you designed it to give us a gain of 10 and you expected 5 volts on the output. Does that make sense? So have I totally confused you? I'm not surprised if it's totally confused. But I just wanted, my main point here is that it's all well and good to do calculations, but you must remember in reality there are constraints. Yep.
In the analogy you just gave, why would it matter? Because wouldn't the current still be at 100 milliamps? So you've got still got maximum current. So you the voltage drop.
Yes, so you've got maximum current, but when I designed this with this 27K and 3K, I expected a gain of 10 on my input of 0.5. I expected this to be 5 volts, right? Now that this op amp can only supply 100 milliamps, and I've plugged in a load which significantly lowers that voltage, you can just see via the calculation, it lowers that voltage, then your op amp won't be amplifying enough for you to hear a difference in your headphones in this case. So in this case, you wouldn't be clipping. In this case, the output would be getting too low that you can't hear it.
Okay, so but if it was, say, 30 amps, so would you have quite?
Yeah, it would be less than what you wouldn't be, you're turning the knob up on the volume, but it's not getting much louder. Okay, so takeaway message, yep, sorry, question? Sorry? All right, so you're right, volume would depend on the current. So in that particular analogy, maybe I wouldn't use the headphone again. I would use something else, another system. But yeah. Yes, where the voltage is the main thing, yes.
In that case, we would assume they were like inefficient headphones, and if we had like 80 ohm headphones,
Yes,
really efficient,
that's right.
then we could do that.
That's right.
Yeah, okay.
Yep. Okay, so takeaway message, op amps can only supply finite current, and if you exceed this limit, the op amp will not perform as you expect. Okay, so this one, is it worth doing this one? Getting you to do it? No. What do I want to tell you out of this one? I might get you to do the last one. This one you can do in your own time. Here's another interesting invention that I just saw yesterday. This is a flashlight, which it's not just a flashlight. It's a flashlight that feels nice and fuzzy, and so you can have it in your bed. You can reach over and grab it. You think it's your soft toy or something. And in actual fact, the flashlight changes its brightness depending on how hard you squeeze on the flashlight. So if you just want a little bit of brightness because you don't want to wake the dog or the baby, then you just squeeze a little bit. But if you want to totally blitz someone, you just squeeze as hard as you can and shine it in their eye. Interesting system. Why did I even show it? One, it's totally superfluous. Two, it's an interesting electrical system that is totally unnecessary because you could build a flashlight using, as you know, an LED and a battery, which you did in your first lab. But this guy actually made it so that it would detect a number of pressure levels that you have on this particular part of the circuit, and he actually used software to interface to that to determine to change the amount of current going into the LED which is shining out. And this was his prototype circuit to do it. So over-engineering at its best, just because you can. Okay, so so that's the reason for this one. So this question, if you do get around to working it out, which I highly suggest before the mid-semester test, gets you to work out what the voltage is relative to the input, again, using negative feedback, Kirchhoff's current law, and asks you for different values of voltage, what will the output be? And this really, which I believe you guys understand already, is that when you design an op amp system, you must consider the allowable output range of the op amp. That means make sure that the output doesn't go higher or lower than the supply voltages, otherwise you get clipping. Very good. Okay. Double op amp, here we go. Okay, let's finish off with this one. So this one, I'm not going to get you to do it melts. I'm going to do it for you so that you can see that double op amps are not scary. Okay? If you see one, you don't go panic. I think last year on the exam, we had this question where you had an op amp going this way and an op amp going that way. And that totally blew everyone's mind for like the first 5 seconds when they go, I haven't seen anything like this before. But it's actually not too bad. So, you talk me through the process. I want to find V0 in the circuit below with relation to V1 and V2. What's the first thing that I need to check? Negative feedback. Is the first one in negative feedback? Yes. Second one? Yes. Note the trickiness. You've got the plus and minus sign on the opposites on different sides. Okay, so this means that the voltages here are equal and the voltages here are equal. Right? Next, what am I going to do in terms of relating V out to V1 and V2? Where should I start? Do you want to start from left to right or right to left? Left to right, okay. So, what do you reckon I should do? Panic? Yep, panic's one. Kirchhoff's current law, I heard. That's probably a good guess. That's because I've been telling you that's all you need to do. All right, so you've got Kirchhoff's current law this way and this way. So, what is the voltage at this point? V1, why? So negative feedback makes V plus and V minus here equal, and V minus is connected to here, so this is V1. So therefore, KCL here says V1 over R2. I omitted the minus 0 because I'm going downwards and there's a ground here. So V1 over R2 plus V1 minus, ooh, whoa, no. We haven't got anything defined here. What do we do? Sorry? Call it A. Excellent. Let's call it VA. All right, so VA over R1 must equal to 0. Excellent. All right, so what can you do here? Well, you can rearrange this so that you get VA over V1 equals 1 plus R2 over R1, right? Yeah? Why would I want to do that? We'll see. Okay, so that's for this bit. Now, what do you think I should do over here? Why don't we do a Kirchhoff's current law over here?
Is it R2 on R1 or R2?
Yep, you're right. R1 on R2. Thank you. I just noticed that. Okay, so over here, why don't we do the same thing? So for this one, this is KCL 1. So this is at node 1. And this is KCL at node 2. Now notice that I strategically picked this node and not this node. I picked this node and not VA because, as you'll see, it helps us to relate V out to VA. So over here, KCL2 gives us, now what is the voltage at this point? No. So here, I'm talking about, okay, I hear V2, V1, R1, so 2. It is, in fact, V2. No, V2 is not equal to V1. Okay, so here's the interesting thing. Okay, so the reason it's equal to V2 is because this op amp is supplying current through the circuit to make sure that this voltage at this point is the same as the voltage at the positive terminal. So therefore you've got V2 minus VA over R1 plus V2 minus what? Give me a letter. V what? O, that's it. VO over R2, right? Equals 0. So what can we do? Well, let's collect up the terms. Okay, so what do we got? We got VO. Let's make VO go to the right-hand side. So therefore, you'll get V2 outside of 1 over R1 plus 1 over R2. Subtract VA over R1 equals VO over R2, because I've taken this term over to the other side. Make sense? And what can I do to just get VO? I can multiply through by R2, right? So I can go VO is equal to V2, and you'll get R2 plus R1, R2 over R1 plus, what's R2 over R2? 1 plus R2 over R1. Subtract VA over R1. Now over here, in fact I got too clever. I'm just going to backtrack and put that V1 over this side, because that means I can directly substitute VA into this, and I would get V1 times outside of what have I got? 1 over R1 plus 1 over R2.
So you've only got 2 different types of resistors in the circuit?
Yes.
Yeah, okay.
Yep, I've only got 2 different types of resistors in the circuit. Okay, and then this can be simplified down to 1 plus R2 over R1 outside of V2 minus V1. Okay, because this can be turned into another factor of that if I multiply through by R2 over R2. Okay, so what is this circuit doing? It's doing stuff, yes. It's not doing nothing unless I've put nothing into it. Sorry? It's changing V out with respect to the resistors. Yes, but I wouldn't give you many marks for that. What is it doing to the inputs? Looking at the difference between 2 inputs and then multiplying it by a gain factor, 1 over R2 over R1. Yeah? So over here, this is the difference between these 2 signals, V2 and V1. And we're multiplying it by a gain. Yes. So you're actually, in actual fact, this kind of configuration is called a differential amplifier. Okay? And differential amplifiers lead me to next week, because they're really, really useful things, and I'll show you how to use them next week. Okay? So, thanks for that. Do that one in your own time. I'll put solutions up, and see you next week.